Okay, so we're going to continue talking about angular momentum. And I had a few students show up at tutoring last night, and they were thoroughly confused, and it was not particularly nice to them. So although I won't call them out by name because that's just rude, I was probably just not in a particularly good mood and maybe took it out on them. So I will still be at tutoring tonight. I might be a little late because I'm still trying to do a bunch of stuff. But now you all know why I'm out. There it is. So I want to go over one of the homework questions because it seemed to be tough and it was giving people some troubles. So we'll try this one out. It was the air table question. And let's start by considering what the air table question asks. It's got an air table, and I was surprised when I thought maybe people don't know what an air table is. So let me see. Hold on. Boom. That's an air table. You know, the pucks and stuff, that's what an air table looks like. So it's got little holes all over it. You see all the little holes? Air comes out of those little holes. And it's like basically trying to say it's a frictionless surface. Yay. Okay, so that's an air table. Now let's imagine this is our air table, and we have drilled a hole in the middle of the air table. And I have a puck, which I assume is like on a string because they tell us it's on a string. So here's my puck. It's round. It's like that. And there's a string attached to it that goes down the hole. So to understand what this really looks like, I think I need to draw it again from the side. So here is the side of my air table. And here is my puck. There's my puck. And the string, like so. So this is 0.5 meters. This is 0.5 meters. They tell me that the puck is traveling a circular path at 2 radians per second and has a mass of 0.2 kilograms. So what they say in the problem is that they're going to grab onto the string. That's a hand. I know it doesn't look like a hand, but trust me when I say that's just a terrible hand. Let's try that again. All right, so it is quite possible I've done worse, but oh, what the heck was that? There's my hand. All right, so we grab on to the side of the string, and we're going to pull downwards on the string while it's spinning, shortening the distance from 0.5 to 0.2 meters with the puck, right here. So that's what's going to happen. The force on the puck comes from the string and is this way. That's the tension. And we're going to apply tension to the string. There's already tension there because it's traveling in a circle. But we're going to apply more tension to shorten the string. But that force, because it's applied along the string, can't cause a torque. Torque equals R times F times the sine of the angle. So, yeah, there's an R. It's 0.5. There's an F. I don't know what it is, but there is one. But the angle is 0 degrees. Sine of 0 is 0, so there's no torque. If you don't understand that, then play it again at half speed, and maybe it'll make more sense. So let's get to this. There's the angular momentum of the system before, and then I pull on the string, shorten it. That has to be equal to the angular momentum of the system after, because there's no net torque on the system. So all I need to do then is consider that there's the moment of inertia before and the angular speed before, because this is how you calculate angular momentum. That has to equal the moment of inertia after and the angular speed after. Why? Because that's how you calculate angular momentum. And the angular momentum hasn't changed. What has changed? This number. The moment of inertia is going to get smaller. The radius is getting smaller. And this is a point mass. And the moment of inertia of a point mass is based on how far away from the axis of rotation it is. Moment of inertia equals mr squared. r is going to get smaller. M is going to stay the same. So because r is going to get smaller and m is going to stay the same, the moment of inertia is going to get smaller. So if the moment of inertia gets smaller and the angular speed stays the same, then the final angular speed is going to have to increase to compensate for the moment of inertia getting smaller. Sorry, I said that wrong. If the moment of inertia is going to get smaller and the angular momentum has to stay the same, then the new angular speed is going to have to get greater to compensate. Here, let's see how it works with the whole mathy math part. So I have as my moment of inertia mr squared, so that's 0.2 times 0.5 squared times the angular speed, which is 2 radians per second. This is the initial angular momentum. This must equal, equal the new moment of inertia, which is mass of 0.2, radius of 0.2 squared, times final angular speed. They have to be equal, so since this got smaller, this is going to have to get bigger. So I'm not going to do the math. I think it's pretty clear that you guys can do the math, so we're going to stop right there. That was the second question on your homework. So there might be more questions, but we're going to go on. So let's go on. So I want to talk about another kind of phenomenon, but to understand it, you have to already have kind of an appreciation for this whole idea of what angular momentum is all about. So the thing is, once something is spinning, it wants to stay spinning. But at the same time, we have some interesting kinds of collisions that occur that don't appear to be spinning but are. So let me give you an idea. Imagine the merry-go-round. We've talked about merry-go-rounds a couple times now, but imagine a merry-go-round. And if you're a kid and you want to spin it, you could stand on the outside and give it a solid push. You know, we know that if you apply that force here at the edge, that would be a torque, and that torque would cause the merry-go-round to spin up. And that one's pretty easy because we know that net torque equals I times alpha. And so our unbalanced torque causes an angular acceleration, and eventually that will lead to an angular velocity. That one's pretty straightforward. But what if the kid decides he really doesn't want to, that he wants to try something else? Another way to spin it up would be for the kid to make a run at it. Maybe the kid hangs back here and he runs and jumps on right at the edge. If you can imagine that, can you imagine that after they jump on at the edge, the system will begin to rotate about the center? Seems plausible. Now, this might not look like it, but this constitutes a collision. But this collision doesn't conserve linear momentum. Let's handle this first. When the kid jumps on the merry-go-round, it's not like the merry-go-round can suddenly fly off in this direction. It can't. So based on like other collisions we've seen where an object strikes another object and they both fly off together, that can't happen. The merry-go-round is firmly fixed to the ground. In fact, when the kid jumps on, there is probably a force on the merry-go-round from the ground in this direction to prevent the merry-go-round from flying away that way. The thing is, that force ensures that linear momentum is not conserved. That force times time causes a change in the linear momentum. impulse. Remember, this is part of our review. There's some review thrown in here for later. This is impulse. Now, this impulse doesn't allow regular translational momentum to be conserved. That's why the system stays in place after the collision. The thing is, after the kid jumps on it, the merry-go-round does spin. So, is there a way to take what we know about the kid's motion and figure out how much angular momentum the kid has? And the answer is yes. But it's a little bit hard to understand, so let me break it down for you. What we say is that the kid has angular momentum. And they have angular momentum because as they're running towards this point, they are, it's as if they are rotating about this point. I want you to imagine a line drawn between that point and the kid. Like, say there's a rope there. As the kid runs, even if they don't jump on the merry-go-round, that rope tends to spin around this point. So let's say they keep going. We see that rope tends to spin around like so. It's as if the kid is causing something to rotate about the pivot point of the merry-go-round. They don't, but it's like they do. I want you to imagine if you were another kid and you were standing here and you were watching this other kid run by, your head would have to turn to track them. Well, it just so happens that the idea that the kid is running towards the merry-go-round and can jump on the merry-go-round actually ends up being as if the kid has angular momentum. Now, how do we calculate this angular momentum? This is called angular momentum for a point mass. That's what we call it. Angular momentum for a point mass traveling in a straight line. So the kid runs towards the merry-go-round. Now, because this is kind of a weird kind of angular momentum, we give it a lowercase l. Boy, that's a terrible lowercase l. Let's try again. A lowercase l. And here's what it looks like. This is going to be tough. It's R times P times the sine of the angle between them. Now, that's technically the definition for angular momentum of a point mass. We'll never use that definition. We're going to use a shortcut. But that definition defines R as an arrow drawn from the center to my guy. P is the momentum of my guy, that MV for him. And the angle is the angle between R and P. That's how we define it. Now, we're unlikely to ever use this definition of angular momentum of point mass. And the reason is because if the kid's running, he's changing that R and P all the time. I mean, look, a few seconds later, he's right here. If he hasn't changed his speed, the momentum is the same, but suddenly R is a lot shorter and the angle is a lot bigger. It just so happens that R and the angle change in the same proportion all the time. Because of that, we will almost always calculate the angular momentum for this problem. And this problem is very rare. Anyways, we'll almost always calculate the angular momentum of a point mass by doing what's called r perpendicular times p. That's right, r perpendicular times p. Memorize this one. This one's the good one. This one's in your equation sheet, but this is the one you want. R perpendicular takes the kid that's running and fast forwards it to the moment he's actually useful. What I mean by that, this was all formulated to help figure out this kind of problem. A problem where we know the kid jumping on the merry-go-round is going to cause the merry-go-round to spin. So in order to find a way to categorize or to quantify what the kid can do to the merry-go-round, this was created to handle this problem. So the kid's not jumping on the merry-go-round when he's over here, when he's sitting over here. The kid can't jump on the merry-go-round until he makes it right to there. Right when he jumps on right here. So just before he actually lands on there, if you'll notice, this will be the point where he's at r perpendicular. His velocity is still this way. It's tangent to our circle. He's at the point of closest approach. That's what I call this, the point of closest approach. If he doesn't jump on and just keeps going, then nothing happens. But if he jumps on, then it's a collision. Now, angular momentum is only conserved in cases where there's no external torque. But Mr. Shelton, you said when he jumps on, there will be a force to hold the merry-go-round in place. That is true. But that force acts at the center of the merry-go-round. And because it acts at the center of the merry-go-round, it doesn't cause a torque. It can't. Torque is R times F times the sine of the angle, and R is 0 for the thing holding the merry-go-round in place. So, because there's no torque, the angular momentum that the kid has before will have to be equal to the angular momentum of the system afterwards. Let's see what this looks like, okay? For this particular example, we're going to use this kid that was running. I'm going to back it all up to that point, but I've got a lot on the screen, so let's just make it all small. And let's erase all this. And let's get a drink of water. All right. So let's say the kid was running at 3 meters per second. Let's say it has a mass of 40 kilograms and is running right towards the edge of the merry-go-round. Let's say this merry-go-round has a radius of 2 meters, my favorite merry-go-round radius, because I always use 2 meters. And let's say that it has a mass of 150 kilograms. And let's say that it is a disc. Okay, let's begin. I want to know, here's what the question will sound like. I would like to know how fast the merry-go-round is spinning if the kid jumps on the merry-go-round. Okay, so we want to figure out first, is this a conservation of momentum problem? And yes, this has all the signs of it. In any conservation of momentum problem, you're looking for a collision. This is a collision. And in this case, the collision occurs because the kid is jumping on the merry-go-round. That's the basics of a collision. So let's go ahead and deal with the fact that it is a collision by doing our mathy math. We're going to say that the angular momentum of the boy, so there we go, angular momentum of the boy is going to equal the angular momentum of the system afterwards. Now, angular momentum of the boy, I should technically say it's R times P times the sine of the angle. We're not going to use that, but that's technically the definition. Angular momentum of the system. Don't make this harder than it is. The system is the boy and the merry-go-round. When the boy jumps on the merry-go-round, they become one object that has a moment of inertia of the merry-go-round, a disk, and the moment of inertia of the kid, who is a point mass. But they will have a single combined angular speed. This is, for all intents and purposes, a perfectly inelastic collision. Now, with that being said, the thing that you do want to consider is that, can you use our simplified version of calculating the angular momentum? Can we use the point mass, the closest approach calculation? Can we do R perpendicular times P? And we can, because they run and jump on the edge. It's not hard to know when to use this one, but as you guys are new to this, and it's not like I'm there are some signs you can look for. For example, if they don't tell you how far away you start, that's a big sign that you can't use this version. If they tell you that you run towards the edge, that's telling you to use this version. If the only thing they give you is the radius and tell you jump at the edge on the radius, they're telling you to use this version. Let me just say, you're almost always going to use this version. So let's handle this. R perpendicular is just the radius of the merry-go-round 2, and the momentum of the kid is just mv, his mass 40, times his velocity 3. This is the angular momentum of the system. And if you work it out, you find out you get that funky unit that we have for angular momentum, that kilogram meter squared per second. Let's look. R is meters, 40 is kilograms, and speed is meters per second. That will work out to be kilograms meter squared per second. So we're all good there. This has to equal, all right, got a lot going on here. In fact, I might want to keep that extra parentheses away. The merry-go-round is a disk, so 1/2 mr squared. The kid is a point mass. That's mr squared, so he's 40 times r, which is 2 squared. All that times omega. So, put a lot of it there. I know it's a lot of numbers, but let's see how fast the system is moving after the collision. 3 times 40, 120, times 2 is 120 times 2 is 240. 240 kilograms meter squared per second. All right, let's just do this in parts. 1/2 times 2 squared is 2, times 150 is 300, plus 2 squared is 4. 4 times 40 is 160. And all times omega. So this ends up being 460, and that's kilograms meter squared, because it's a moment of inertia. And there we go, 240 kilograms meters per second squared. There we go. So, all right, I wrote out the units because I wanted you to see that, what I do here. Let's fix that. That's not squared. Let's rewrite it. Kilograms meters squared per second. There. That's what I want to see. I want you to see kilograms cancels, meter squareds cancel. So we're going to be left with units of nothings per second. And we know when we're talking about rotation, if it's nothings per second, it's radians per second. So solving for omega, I get 240 over 460 radians per second. All right, that ends up being 0.52 radians per second. And, that's not particularly fast. 0.52 radians per second, that's, divide by 2 pi will give you your rotations per second. So he's not going to have a particularly fun ride doing it this way. But this is the result of the collision. And let's face it, he's much smaller than the merry-go-round. So because he's much smaller than the merry-go-round, it's not like he can make it go super, super fast. Now, he could, after he jumps on the edge, walk his little butt to the center. That's the problem we did yesterday that a lot of you are having trouble with. If he walks to the center, the system's going to speed up. And it's not going to speed up because he's adding momentum to the system. The momentum won't change if he walks to the center. The system's going to speed up because as he moves to the center, he is reducing the moment of inertia of the system, and the speed has to increase to compensate. So again, he's just jumped on there. And because he's jumped on there, now we have a new thing going on. We've got a kid on the end of the merry-go-round, and the merry-go-round and the kid are both traveling around in a circle at a speed of 0.52 radians per second. And let's say the kid decides to, walk to the center like we've been talking about. So he walks to the center. Well, there's going to be the angular momentum before he walks to the center. That has to equal the angular momentum after he walks to the center. Now, we already know the angular momentum. We calculated it already. It was the angular momentum the kid had before he jumped on there. But I know you guys won't believe me. It was all here just a few seconds ago. If I back it up, look, it's all right there. The angular momentum of the system was, and I'll point it out, this. That's how much angular momentum there was. However, let's treat this like a brand new problem. We know it's got to be 240. We'll treat it like it's a brand new problem because some of you don't really follow that. That's okay. We're going to just treat it like it's a brand new problem. So we'll start with I of the system before, omega before, equals I of the system after, omega after. So I before this thing. That's the moment of inertia of the disk. 1/2 times 150 times 2 squared. Plus the moment of inertia of the kid, 40 times 2 squared, all times the angular speed, 0.52. Now look, when you do this, you're not going to get exactly 240 because we rounded. And because we rounded, we're going to get something a little bit less than 240. But let's just say, because I still have it in my calculator, this comes out to be 240. You should prove that to be true. This has to equal the angular momentum after, but afterwards, although the disk hasn't changed, the kid is walking to the center, so he is going to go to the center of the ride, which means basically he's wiping out his moment of inertia, wiping it right off the equation. So we had a moment of inertia of about 460, but after he walks to the center, we're going to have a moment of inertia of about 300. So this will be 240 equals 300 times omega A after. So omega A, 240 divided by 300. 0.8 radians per second. So he can cause the system to speed up just by walking to the center. Again, I point you to the video I posted yesterday of the kid, or the guy, who was on the merry-go-round. He leaned back, increased the moment of inertia, and the system slowed down. He leaned in and walked to the center and decreased the moment of inertia, sped the system up. All right. So let's try one more, maybe increase the difficulty a little bit. I don't know if that's possible or whether you'll freak out, but I want to try one more of these. And I like this one because I think it's like, I don't know, I think it's like something that could be on a test. They've never asked one like this, but they could. Imagine I have a puck and another puck. And let's say that the pucks are the same size. So there. And one of them has one kind of Velcro, and the other one has the other kind of Velcro, so that when they meet in the middle, they will stick together. Let's say this sucker is 2 kilograms traveling at 3 meters per second, and this one is 2 kilograms traveling at 3 meters per second. If we advance a few moments into the future, we will have the 2 pucks right here. Like so. And they will stick together right there in the middle. What do you think is going to happen? I hope you think that they will spin, because that's what's going to happen. We'll say this is one of the air tracks and there's no friction at all. Now, what's interesting is if you look at the momentum of this system, the momentum of the system, there are 2 objects. There's mv for this object and mv for this object, and add them up, you get 0. Why? Because one is traveling to the right in the positive direction, and one is traveling to the left in the negative direction. So 2 times 3 plus 2 times negative 3 equals 0. This is why they stay still after they collide and just rotate about the center of mass. However, clearly they have angular momentum after the collision, so they must have angular momentum before the collision. So, believe it or not, we're going to use the same idea as before to calculate the angular momentum of the system before the collision, and then compare it to the angular momentum of the system after the collision, because the angular momentum of the system after the collision should be the same as before. So angular momentum, r perpendicular times p. Now you might be saying, well, how do you do r perpendicular? Well, we advance the problem until they touch. And when they touch, r perpendicular is the radius of one of the disks. That's what r perpendicular is going to be. So let's say the disks have radius r. And I'm doing that on purpose, so just bear with me. I want you to see something. Now, the reason I say that it's r is because r perpendicular is the distance from the center of the axis of, I'm sorry, I got tongue-tied. R represents the distance from the axis of rotation to the object, and our axis of rotation is going to be in the middle, and our object's center of mass is in its middle. So although I drew the arrow the other way, this is truthfully the direction that I should draw r perpendicular. That part doesn't matter. It's still just the radius of the disk. Now, again, how can I know to use the radius of the disk? Because technically it's supposed to be r times p times the sine of the angle. And it's not like I told you what that distance was, nor was it me telling you that angle. I didn't give you either of those. And although I didn't give you what the radius is, if you want, I can tell you it's like 10 centimeters or something like that. I'm telling you that's going to cancel out later, and I want you to see that. So if I leave it as r, you'll get to see it cancel out, and that means a lot to me. Just humor me. I'm talking to a black box. It's not like I'm talking to any people. All right, let's begin. Angular momentum of thing number 1. It's let's start with r. That's r perpendicular times the momentum, which is just mv. So the angular momentum is r times 6. And it looks to me like it's causing motion in a clockwise, or using my right hand rule, into the page kind of way. So I'm going to say into the page positive. The other one, I know it's got a negative velocity, but technically it also has a negative r. But more importantly, when it gets there, it's going to cause a rotation in this direction as well, which makes this guy's angular momentum r perpendicular times mv. And for you guys who really want to know, well, where'd that negative sign go? Okay, we'll make this r negative because on the bottom side of our axis, and now you can put that negative sign in there. But it makes the same direction rotation, so the angular momentum needs to be still into the page, which I said was positive. Either way, the total angular momentum is going to be 6r plus 6r, which is 12r. All right, so this is the part where those of you who struggle, back up and listen to all of that over again. Follow it through, try it on your own. But for you guys who are doing okay, let's advance. The system is now rotating. So we have this combined system that has a total angular momentum of 12r. And now what I'd like to know is, what is the angular speed of this rotation? Well, to do that, this is where it gets a little tricky. I have a rotating system now. So we should probably take that into account. Our system has a moment of inertia. We're going to have to find out the moment of inertia of our system. So let's take a look at the moment of inertia of our system. These are disks. So they have a moment of inertia of 1/2 mr squared about their center. But they're not spinning about their center. They're spinning about a point on the edge. So since that's the center of mass, I will have to use I parallel to find the moment of inertia of my system by shifting from the center to the edge for each disk. That'll be 1/2 mr squared, and I'm shifting it an entire radius. So each disk is going to have a moment of inertia of 3/2 mr squared. And how many disks are there? There are 2 of them. This is the moment of inertia of the system. And that is 3 mr squared times omega. And what does that have to equal? 12r. But wait, there's more. The mass of the disk is 6. There we go. 3 times 6, 18. 12 divided by 18. So I'm going to get 12r divided by 18r squared, and that equals omega. So I can cancel out a 3 from each of those. Get a 3 goes in 12 4 times. Actually, I can cancel out a 6 from both of them. Let's do that. We'll cancel the 6 out and get 2/3. And we cancel out one of the r's. So this becomes 2/3r. So I wanted to get to this point because I wanted to show you that our angular speed is based on how big r is. The mass actually canceled out in this. That's why I was able to get rid of the 6. And although the linear speed made a difference, the linear speed happens to be in here, it's r that's kind of funny. If you make r bigger, the system oscillates slower. Make r smaller, it goes around faster. So I think having it in terms of r is kind of interesting because we kind of have this idea of how fast it's going to spin. If we'll make it spin faster, use smaller disks. In fact, it doesn't have much to do with the weight. It's kind of interesting. Anyways, that was my next sample. And now that I know there's only 3 3 minutes till the bell rings. This assumes you guys start from the beginning. You got good start here. I'm going to post a little bit of homework with this. Give it a try. It's not going to hurt you. And I will be available tonight. Tonight. Although I'm recording this on Monday, I'll be available Tuesday at 7 p.m. So if you guys want to log in and, ask questions, I'll be here for that. Alrighty. Fun times. Talk to you later. Bye.